This video contains solutions to sample problems from section 3.2 on problems involving trigonometric integrals. So we're going to cover a lot of the different cases, especially integrals involving sine and cosine, and then a little later integrals involving secant and tangent. Obviously, I can't do every possible case for you, but I'll show you a lot of different techniques that come up. This is probably the simplest example here because we have our functions sine and cosine, and we're relying on the fact that we know that the derivative of sine is cosine, and that the derivative of cosine is sine. And so because we have a single copy of cosine and everything else in our integral is in terms of sine, we're going to use a substitution u equals the sine of x. du equals cosine x dx, and so this is a simple substitution and gives us the integral of u to the fourth du. That's just 1/5 u to the fifth plus c, which is 1/5 sine to the fifth of x plus c. Doesn't really get much easier than that one. All right, so now we have sine and cosine, but they're both raised to powers. Now, the good news for us is that both of these powers are odd. So when you're looking at sine and cosine, you're looking for odd powers. When one of the powers is odd, that's the function that we're going to focus on. Here, they're both odd, so there's actually two different ways that we could do this problem. So I'm going to focus on the lower odd power because that's going to give my answer, make it a little bit simpler. So the sine cubed, the reason why oddness is helpful is we're going to take one of those copies of sine of x and factor it out and move it over next to the dx. And so this is going to be my du, which means my u is going to be the cosine of x. Now that's not exactly my du because the derivative of cosine of x is negative sine of x, but that's the idea. So in addition to having sine of x dx, I'm going to have to put in a factor of -1, which means I'm going to have to put another factor of -1 out front of my integral to balance that out. Now my goal is to write the rest of my integral in terms of this u that I substituted in terms of cosine of x. So cosine to the fifth of x, that's already in terms of cosine. What about sine squared of x? Now's where we're going to start relying on some trigonometric identities. Specifically, we're going to use what we call the Pythagorean identity, which is that the sine squared of x plus the cosine squared of x equals 1. We're going to manipulate that a little bit, subtracting cosine squared from both sides, and writing sine squared equals 1 minus cosine squared. So we have that -1 out front. We've got sine squared of x, which is 1 minus cosine squared of x. We've got cosine to the fifth of x. And then we've got our du, which is negative sine of x dx. So everything's in place for us to convert this integral into a u integral. So we've got -1, that's 1 minus u squared, that's u to the fifth, and then du. Now let's multiply all this stuff together before we integrate. The -1 is going to switch the order of that subtraction. Then when we distribute the u to the fifth, we get u to the seventh minus u to the fifth. Antiderivative of u to the seventh is 1/8 u to the eighth. Antiderivative of u to the fifth is 1/6 u to the sixth plus c. And then the only thing left to do is to substitute back in. U was cosine of x. So that's 1/8 cosine to the eighth of x plus 1/6 cosine to the sixth of x plus c. Now it is possible to do this problem focusing on the cosine to the fifth, separating out one copy of cosine and then substituting u equals sine. If you do it that way, you will get a valid answer to this question, but it won't look at all anything like this answer that I just got. And that's one of the tricky things that happens with trigonometric integrals sometimes, is you get two different looking answers that are both correct. So just keep an eye out for that and be aware of that. Okay, so this example, we look at our powers of cosine and sine, and we see that only one of them is odd. So we don't have the kind of choice that we had in the previous problem. Now we really are forced to use the cosine and substitute u equals sine. So again, our process is to look at that odd power, separate one of the copies of that function, and move it over next to the dx, and then substitute u equals the other function. So in order to get du to equal cosine of x dx, I'm going to have to use u equals the sine of x. So if that's the substitution I'm going to use, that means everything else in my integral has to be in terms of sine of x. Sine to the fourth is already in terms of sine of x, so I need to rewrite cosine squared. Using that Pythagorean identity again, cosine squared of x is 1 minus sine squared of x times sine to the fourth times cosine of x dx, which is going to turn into my du here in a second. So when I do my substitution, I get 1 minus u squared, u to the fourth, du. Distribute my multiplication, I get u to the fourth minus u to the sixth. Take my antiderivative, I get 1/5 u to the fifth minus 1/7 u to the 7th plus c. Substitute back in u equals the sine of x. So that's going to be 1/5 sine to the 5th of x minus 1/7 sine to the 7th of x plus c. And that's our final answer. Okay, so what do we do when both of the powers are even? Here we use yet another trig identity, and in this case we use what we call the half angle formulas. There are two of them, one for sine and one for cosine. The half angle formula for cosine says cosine squared of x is 1/2 times 1 plus cosine of 2x. Sine squared of x is 1/2 times 1 minus cosine of 2x. So we've got those two formulas, and those are going to be what we use to convert this integral into an easier to use integral. So because all of our powers are even, we're going to break everything up in terms of pairs of these functions. So cosine squared, sine squared, and then another sine squared. And each of those is going to get replaced using these half angle formulas. So we get 1/2 times 1 plus cosine 2x, 1/2 times 1 minus cosine 2x, 1/2 times 1 minus cosine 2x, and then dx. So now we're going to multiply that out. That's going to require some algebra, which I'm going to sort of glide over for you just to make this problem not take quite so long. But we've got 3 factors of 1/2, which means we've got a big factor of 1/8 sitting out front. And when we multiply all that stuff out, what we end up with is 1 minus cosine 2x plus, minus cosine squared of 2x plus cosine cubed of 2x. And so that's really 4 separate integrals that we're going to have to do one at a time. So let's do those. So we've got 1/8 times the integral of 1 dx. Not too much going on there. That's just going to be 1/8 x. And then we've got 1/8 times the integral of cosine of 2x dx. Again, not too hard there. That's a simple u equals 2x substitution. And so that's going to give us minus 1/16 sine of 2x. Then we've got minus 1/8 times cosine squared of 2x. And that's an example where we have a sine-cosine integral where all of the powers are even. We've got cosine to the 2. We don't have any sines, which you can think of as sine to the 0, because there aren't any sine functions at all. So that means we're going to have to use the half angle formula again. Now here's some place where folks get sometimes tripped up. So if cosine of x is 1/2 times 1 plus cosine 2x, what's cosine squared of 2x? Well, if the angle gets doubled, then if I apply my half angle formula to this angle, 2x, then I'm going to get cosine of 2 times 2x, which is cosine of 4x. So whatever the angle is in your parentheses, if it's just x, you double it and you get 2x. But if it's already 2x, then you double it and you get 4x. So when I rewrite this integral, I get minus 1/8 times the integral of 1/2 times 1 plus cosine of 4x. So that's going to be minus 1/16 times the integral of 1 dx, and then minus 1/16 times the integral of cosine of 4x. When we take the antiderivative of 1, we get minus 1/16 x. Then we take the antiderivative of cosine of 4x. That's going to give us 1/4 sine of 4x. 1/4 times the 1/16 that we already have there is a 1/64 sine of 4x. So we've got our pieces of our answer are coming together here. And that's what we've got so far. And now what's left is this guy. So now we have to integrate 1/8 times cosine cubed of 2x. Now here's an example where we have sines and cosines with an odd power of cosine. So we're going to apply the method that we learned in the previous examples. We're going to split off one copy of that cosine of 2x. And we're going to use that to do a substitution. In this case, u equals the sine of 2x. Because then du will be 2 sine 2x. We're going to rewrite cosine squared of 2x as 1 minus sine squared of 2x. Cosine of 2x dx is going to be part of my du, except I'm missing a factor of 2, but I can put that in as long as I multiply by a 1/2 out front. So this is going to be 1/16 times the integral of 1 minus u squared du. That's going to be 1/16 u minus 1/16 times 1/3 u cubed. And then finally, I'm going to get a big ol' plus c at the end. So what was 1/16 u? So 1/16 u was 1/16 times the sine of 2x. And then 1/16 times 1/3, that's 1 over 54. 1 over 48. And then u cubed is sine cubed of 2x plus c. Now we can simplify this a little bit, so we can take the 1/8 x and the 1/16 x, and those combine and give us positive 1/16 x. We can also take this negative 1/16 sine of 2x and this positive 1/16 sine of 2x. Those actually cancel out. And then what we have left is minus 1/64 sine of 4x. And then minus 1/48 sine cubed of 2x plus c. And that is our final answer there down at the bottom. So a lot of steps here. So it's kind of nasty when you don't have any even powers at all. Oh, sorry, when you don't have any odd powers at all, it's pretty nasty. When all the powers are even and sines and cosines, these can be nasty. All right, so the next several examples are going to involve secant and tangent. And so at first glance, we might look at this and say, uh-oh, both of those powers are even. This is going to be a nasty example like the one that we just got done doing. But actually, it won't be that bad because we're going to be relying on the derivatives of secant and tangent, which aren't quite the same as sine and cosine. So the derivative of tangent of x is secant squared of x, and the derivative of secant of x is secant times tangent of x. So which examples are easy and which are harder for secant and tangent is not quite as easy as just looking at even versus odd. In this case, I have a secant squared of x, so all I need to do is switch the order here and move that secant squared next to my dx, and this can be my du if I let u equal the tangent of x. So if I let u equal tangent of x, du is secant squared of x, and this is an easy substitution. So this is just u to the 4th du. That's 1/5 u to the 5th plus c. That's 1/5 tangent to the 5th of x plus c, and we're done. Or what about an example like this where all we have is secant? And so now we're going to need to use our Pythagorean identity, but the version of that Pythagorean identity that involves secant and tangent. So we already knew that sine squared of x plus cosine squared of x equals 1. The relationship between secant squared and tangent squared is that secant squared of x is equal to 1 plus tangent squared of x. So not quite the same thing. But what this lets us do is separate out a secant squared. So we've got secant squared of x times secant squared of x. This secant squared of x times dx, that's going to end up being my du. And the first secant squared of x, I'm going to rewrite that as 1 plus tangent squared of x. So if I substitute u equals the tangent of x, similar to what we just did in the previous example, then this is going to give us 1 plus u squared du. Antiderivative of 1 is u. Antiderivative of u squared is 1/3 u cubed plus c. So this gives us tangent of x plus 1/3 tangent cubed of x plus c. What about just tangent to the 4th? Well, you might think, oh, well, secant to the 4th wasn't so bad. What about tangent to the 4th? Unfortunately, it's not really symmetrical. It is going to work out a little bit differently. But we're going to have a similar strategy where we're going to split off tangent squared and tangent squared. But unfortunately, tangent squared isn't really the derivative of anything useful, and so we're not going to be able to just do a simple substitution here. But we are going to rewrite tangent squared, one of these tangent squares, as secant squared minus 1, if I just subtract 1 from both sides of that identity. And now if we break this up into two separate integrals, we've got secant squared times tangent squared, which I'm going to rewrite in this order, tangent squared times secant squared, minus just the integral of tangent squared. Now this one, this first integral, I'm going to be able to do a u equals tangent of x substitution. The second integral, I'm going to use my identity again to rewrite tangent squared as secant squared of x minus 1. And I can integrate secant squared, because that's just going to give me tangent of x. I can integrate 1 because the antiderivative of 1 is x. And so that's just going to give me plus x because I've got two negatives there, minus and minus. And then I've got my plus c at the end. So what about this first integral? Well, if du is tangent of x, or if u is tangent of x, then du is secant squared of x. So this is just the integral of u squared du. That's going to be 1/3 u cubed. And so that's going to be 1/3 tangent cubed plus all that other stuff. So that's my answer for this one. All right, what about this last one here? So this is one of the examples of a secant and tangent integral that is probably the most challenging of these examples. So it turns out that when you have this type of combination of evens and odds, this is about as bad as it gets. So what we're going to need to do is, perhaps surprisingly, we're going to need to use integration by parts here. And it's going to need to be integration by parts in kind of a tricky way. So I'm going to call this integral I. And so we're going to rewrite this integral, first of all, split off one of the copies of tangent. So we've got tangent, and then we've got secant of x times tangent of x dx. And hopefully you recognize that secant of x times tangent of x, that's the derivative of secant. So if we use integration by parts here, we're going to let u equal the tangent of x. We're going to let dv equal secant of x tan of x dx. So that du is the derivative of tan-ish, which is secant squared, and v is the antiderivative of secant x times tangent x, which is just secant of x. So when I use integration by parts, I end up with uv, so that's secant x tangent of x, minus the integral of v du, so that's going to be secant times secant squared, which I'm just going to go ahead and leave factored like that because we're going to split them apart in a second anyway. So secant of x times secant squared of x. And we remember that we can rewrite that secant squared of x as tangent of x squared plus 1. So we've got secant x tangent of x minus secant of x times 1 plus tan squared of x. And if we break that up into two separate integrals, we get secant x tan x minus the integral of just secant x all by itself, we'll talk about that in a second, minus the integral of secant x times tan squared of x. And you might recognize this integral is I, the original integral again. So if that's on the left-hand side of this equation, because that's what we started with, we can add that to both sides and get 2I equals secant x tangent x. Now, what's the antiderivative of just secant all by itself? Well, you might have learned this in Calculus 1, but that one's actually a little bit of a nasty formula as well. But the antiderivative of just secant of x is natural log of the absolute value of secant x plus tangent x, and then plus c. So now the only thing left to do is to divide both sides by 2. So we get that our integral that we're working about is 1/2 secant x tan x plus minus 1/2 natural log of secant x plus tan x plus c. And that is our answer there. So integration by parts pops back up. We haven't talked about that much in this section, but we needed it for this example, and hopefully this makes some sense for you. So in this video, you've seen lots of different strategies for integrals involving sines and cosines and integrals involving secants and tangents. So I hope this was helpful.